Hi guys, in this video we are going to do preparation for your paper 3, Ujian Amali Sains Physics paper 3. I'll be doing videos for chemistry and biology as well. You can look out for those videos, just search for it under my channel or I'll leave the link in the description once it's done. But in this video we're going to focus on physics, and the sample topic that I've chosen is Archimedes principle. Now, first of all, I want to make it very clear, this is not a prediction. Okay, this is not a prediction. I'm not predicting that this will come out. So this is just a sample topic that we're going to discuss. Don't fully rely on this. Don't think that this is definitely coming out. Please be prepared for other topics as well. Okay, please be responsible. All right, now, so let's go to this Archimedes principle. So let's look at the theory first. There are two very important formulas that you need to know for this topic when it comes out, if it comes out in your paper 3. So the first formula is FB. FB represents buoyant force. So if you remember, Archimedes' principle is about buoyant force, right? When an object is partially or fully immersed in a liquid, then what will happen is there will be an upward force, buoyant force acting on the object that is equals to the last part of Archimedes' principle, that is equals to the weight of the liquid displaced. Weight of liquid displaced. So that would be FB equals to WD, weight of liquid displaced. So what is this weight of liquid displaced? I'm going to tell you in a while. Okay, we're going to discuss this setup here. So the second important formula, there's another way that we can find buoyant force, which is we use the weight in air minus the weight in water. Weight in water is sometimes called the apparent weight. Okay, weight in air minus weight in water. So these are the two formulas that you absolutely must remember if this comes out in paper 3. Right? Okay, so there is one experiment in this topic in your textbook, and that would be this is the setup that is used. So in this setup, you can see, okay, so let's look at the apparatus first. Apparatus and materials. So we have the basic, the retort stand, and then you have a wooden block here. Okay. Okay. So what I want you to pay attention to is number one, this Eureka can. So a Eureka can is basically a container, a metal container or a glass container. It doesn't matter, but it has a spout that is coming down like this. Right? So what we do with the Eureka can is we fill it up to the brim here. It can't go past this, because if you fill any more than this, if you fill water any more than this, it's going to start spilling out. And that's the key here. So we fill it up to this point, right? Once you immerse this object, whatever object it is, in this case, it's a slotted weight, whatever object you immerse in this liquid, right? The liquid will start pouring out. And so this is the liquid that has been displaced by the object. The object has displaced this liquid. It has replaced it in its physical position. It has taken its place and replaced it. Displaced. So this is the liquid displaced. So here we are using water. So this is the water displaced. Right? So that's what we mean by water displaced. Okay. So another thing that's important here, there are two measuring instruments that we're using here. Number one is the spring balance. So the spring balance is, of course, to measure force, right? Spring balance measures force. But actually, what does the reading reflect? Okay, so let's do a very simple free body diagram here of this slotted weight. So the slotted weight, it has weight acting on it downwards. Now, what is pulling it upwards? It is the tension from the spring in the spring balance. The tension of the spring is pulling it upwards. So in this situation, the reading of a spring balance, the reading that we get here is actually not the weight. It's not the weight directly. The reading that we get is actually the tension. Right? Please make sure you understand this. The reading that we get is actually the tension in the spring. However, this is an object that is in equilibrium of forces, which means the tension is in fact equals to the weight when it is in air. So the reading that we get here is in fact the weight, yes, but not directly. This is important. So in air, there's no problem because there are only two forces acting on this object. Once you immerse it in the liquid, what are the forces? Why don't you try to figure it out yourself first? Okay, we still have the weight, of course. We still have the tension. But now, since it is immersed in a liquid, we have an additional force, right? We have the buoyant force. Now, once again, this object is in equilibrium of forces because it's not moving. Therefore, the sum of the forces acting upwards, T and FB, the buoyant force, FB is the buoyant force, yeah? This must be equal to the sum of force acting downwards, which is W. So the reading that we get here, remember, the reading that we get is only tension. So T will be W minus FB. So this would not reflect the actual weight of the object, but the weight of the object minus the buoyant force. So this is what we call the weight in water, or the apparent weight. Apparent weight. Right? So weight in water. This is what we call the weight in air. Okay. So how do we get the buoyant force from these two readings? So from these two readings, what we can do is you can take the difference between this and this. That is the buoyant force. So we take weight in air. So buoyant force, one of the ways is on the right side. Weight in air minus weight in water. Okay. So now there is another way to find the buoyant force. That is, we directly measure. Now, remember what's Archimedes' principle. Archimedes' principle states that at the end of it, it states that the buoyant force is equals to the weight of the liquid displaced, isn't it? So we have already collected the liquid displaced here. So how to find the buoyant force? Get the weight. This is why we have an electronic balance here. The electronic balance is to get, of course, the electronic balance will not directly give you weight. Yeah, this will give you the mass of the liquid displaced. And when you want to find the weight, then you have to multiply by G. Okay, although we use 9.81 in paper 2 and paper 1, pay attention to the question. They might tell you to use 10. Right? They might tell you to use 10. In your textbook, it says, for this part, it says assume, in your textbook, yeah, it says assume 1 gram is to 10 newtons. So you just multiply by 10. Okay, this is what it says in the textbook, but please be careful. Please read the question carefully, follow the instructions given. Okay, all right. So then you would get the weight. So that's another way. That's another way that we can find the buoyant force. Weight of water displaced. All right. Okay. By the way, class, this is my usual notes for my class. If you all are interested in joining the class SPM preparations, exam drills, you can just straight away go to mrrueltuition.com, mrrueltuition.com, and you can sign up right away. And you can join immediately. You don't have to contact anybody. Everything is automated, right? Okay, so let's continue. Now, so this is the setup, and this is how we can get buoyant force, right? Okay, so now I have a sample question here. Okay, my sample question. So, look at the question. Now, you are required to conduct an experiment to study the relationship between. Whenever you get this format, you are very, very, very fortunate. This is the best format that you can get of question, because what comes after between will be your MV and your RV. And the first thing you need to do when you do your paper 3 is discover what is the MV and what is the RV. What is the manipulated variable MV and what is the responding variable RV? First thing. So if they give you the question in this format, that's very simple. So now the weight of liquid displaced and buoyant force. So one is the MV, one is the RV. Okay, so usually what we do is, which one is MV, which one is RV? You determine by saying which is the one that we change at the beginning, which is the one that we modify at the beginning of the experiment, that would be the MV, which is the one that we collect at the end of the experiment, that would be the RV. Usually that is the case. But this experiment, your textbook is a little bit unique. Okay, it's a little bit unique because technically both of these we get at the end of the experiment. Okay, technically we get it at the end of the experiment. So basically, class, the procedure is very simple. Okay, you're basically going to do this. So we are going to hang it in the air, get the weight in air first, and then immerse it in the liquid, and then measure the weight in liquid. Right? So we're going to measure two things here. So how do we get the buoyant force? We have to calculate using the formula. We have to use WA minus WD, because these are the two readings that we're going to take. We are going to get weight in air, weight in water, and then you're going to subtract to get buoyant force. So this is to get buoyant force, right? And then the final reading that we will take is the weight of the water displaced, or this is also calculated actually. We will take the mass and then times 10. So you get the weight of the liquid displaced, right? Okay, so we're going to take 3 readings. Okay, 3 different readings. Okay, so here the manipulated variable according to your textbook is the weight of the liquid displaced. Now, usually the first one that follows the between is the MV, usually. All right. So if you're confused, if you really don't know, then if you had to guess, then that is probably how I would guess. Okay. If I had to guess. Now, so the first thing you do is figure this out, MV, RV. So even if they don't ask, yeah, because we need the MV and the RV to answer inference and hypothesis. Okay, so you always figure out MV, RV first. So manipulated variable here would be weight of the liquid displaced. The responding variable would be the buoyant force. Okay, don't worry about the fixed variable first. I'll teach you about that later. So using these two, we can now answer inference and hypothesis. So inference in physics is very unique. It is unlike chemistry and biology. Okay, so inference in physics, you can use 2 formats. You can either use MV affects RV, or you can use RV depends on MV. These are the 2 formats that you use for inference. Both are acceptable. Okay. So if we choose MV affects RV, it's a very simple case once you have identified your MV and RV. So MV will be weight of liquid displaced. So weight of liquid displaced affects RV. RV is buoyant force. So this will affect buoyant force. That's it. Simple as that. Done. That's your inference. Okay. The other format will be another format. So this is a separate answer. Don't have to write both. Just choose either one. All right. So RV will be buoyant force. Buoyant force depends on MV, weight of liquid displaced. That's it. Okay. Now, hypothesis. What is the format for hypothesis? So this is standard across all the subjects here. When MV increases or decreases, RV increases or decreases. This is the format that I teach my students because of grammar. Grammatically, this is the easiest because in everything there is increase, and everything that is quantifiable, you can say increase or decrease. If you use greater or lesser, sometimes it's not so suitable. But you could use that format as well. The greater or the lesser, MV, comma, the greater or lesser RV. No problem. No problem. Okay. So here, what is the MV again? When the weight, the weight of liquid displaced. So we do when the weight of liquid displaced increases. So you choose either increase or decrease. Then the RV, so the buoyant force. What will happen to the buoyant force? So this is where you have to make your educated guess, right? Based on the theory, okay, what will happen if there is more water displaced? What will happen to the buoyant force? It will increase as well. It will increase as well. So don't use relationships here. I mean, don't use proportionality here. Don't say weight of liquid displaced is directly proportional. Okay, don't say that. Here we are basing it on what might happen during the experiment. We don't know whether it's directly proportional until we draw the graph, right? So before you have the graph, you cannot conclude that it's directly proportional. You can only say when this increases, this increases. Based on the graph, if it is a directly proportional graph, that means if it's a straight line that passes through the origin, then you can conclude at the end that it is directly proportional, but not at this point. No. So you just say increase, increase. All right. Okay. So let's go to the fixed variable. So when you are choosing the fixed variable, if there is a formula, we always refer to the formula to look for the confounding factors, the other factors that can affect the outcome. So if we look at the formula for buoyant force is rho Vg, right? Rho Vg. Okay. So what can affect the buoyant force? The volume of liquid displaced. Okay. This is the volume of liquid displaced, right? This is not the volume of the object. If the object is fully immersed, then yes, they are the same thing. The volume of the object is equals to the volume of the fluid displaced because the entire object is already immersed. Everything has been everything is submerged under the water, right? Okay. So G is a constant. We are not going to change G, right? As long as we are doing it in the same location, G is constant. Volume it is being manipulated here. It is being manipulated by this is the RV. This is the MV, in fact, because this will represent the weight of liquid displaced. So the greater the volume of liquid displaced, the greater the weight of liquid displaced, right? Okay, so yeah, this is related, and this is our MV. What is the RV here? So what are the other factors that can affect this experiment outcome? It would be the density of the liquid. The density of the liquid used. If you use a liquid of different density, then it will change the buoyant force. It will also affect the buoyant force. So we need to keep the density of the liquid constant. So the fixed variable, the way that your textbook puts it, is density of water. Density of water. All right. Okay, now let's go to the next part. Draw the experiment setup for this experiment. Okay, this is very possible. Okay, last year it came out for bio. They didn't give any procedure, but they asked to draw the apparatus setup for the experiment. So that would be considered unguided based on my current understanding of guided and unguided papers. That would be an unguided one because procedure is not given, but they asked to draw the apparatus. Please make sure you know how to draw the apparatus, just in case, the apparatus setup, just in case, right? So maybe you can pause the video at this point and try drawing it yourself. Okay, once you're done, then you can check with this. So you would need both the diagrams, one in air and one immersed in the liquid. Okay, to be safe, because I'm not sure what the requirement of the mark scheme would be on this one. We have not been tested on this before, right? So to be safe, just draw both. By right, you could just draw one and then you could explain the steps where you immerse later on. So by right, one should be enough, but just in case, just do both, right? Okay, so then we go on. Okay, so this is the part. Plan the experiment using the apparatus and materials provided. Plan the experiment. Now, this is also in the event that they don't give you the procedure. They might ask you to plan the experiment. There are two ways that they can ask this. One is they only ask you to list the method of handling the variable and the precautionary steps. Methods of handling variable and precautionary steps. Now, I've already touched on this on previous videos on paper 3 tips, right? You can look at that. You can go to last year's video and check how that is done. But today I want to teach you the full one. How do you write a full complete procedure? Just in case, right? So you follow 4 steps, 4 simple steps. Right? When you want to write procedure, the procedure must contain these 4 things. Number 1, all the measurement and preparation. So first step will be measure and prepare. And then after you've measured and prepared everything, then you have to start the experiment. So what is the action that you perform to start the experiment? After you start the experiment, then we need to start collecting data. So that would be observe and record. So we observe and record, or sometimes it's not observation, sometimes it's a measurement. Measure and record. Whatever data we are collecting, that's data collection, right? And then finally, we may need to repeat based on the manipulated variable. So you repeat the experiment, but change the manipulated variable to a different value. Basically, you just follow these 4 steps, you will cover everything. Okay. So again, why don't you try to pause and try writing it yourself first. Okay, so let's discuss this. So what do we need to measure or prepare? Now, a good guideline for you would be the diagram, of course. That's why the diagram is very important. If you can remember what the diagram looks like, you can sort this out very easily. Okay, so based on the diagram, what do we need to do? What do we need to do based on this? So we need to hang the slotted weight on the spring balance, put the spring balance on the retort stand, right? And then you have to place the beaker here on the electronic balance. You have to set up the Eureka tin, fill the Eureka tin with water, but this step is not mentioned in your textbook. But just based on the diagram, I'm saying based on the diagram, you can see clearly what to do, right? Place the Eureka can on a wooden block. So you can write all this down just by looking at the diagram. It's very simple. So again, diagram is very important. Diagram is very important. Okay, once you've gotten all that down, okay, so now let's try to fill it up. Yeah. So measure and prepare. First, we hang the slotted weight. Okay, so we hang the slotted weight on a spring balance and then hang the spring balance on the retort stand. This is the first step. This is step 1. Okay, then step 2. After you've done that, we have to now remember how we are going to get the buoyant force. We are calculating the buoyant force here by getting the difference in the weight in air and weight in water, right? So that means before we immerse it in the water, before we immerse it in the liquid, we need to get the weight as it is now, the weight in air, so that we can calculate the buoyant force later on, right? So this will be weight in air. Okay, so record the weight in air, WA. So use the symbols, use the symbol. It will help you later on when you are tabulating data and when you're doing the graph. Okay, place the beaker on the electronic balance and reset the reading to 0. So we are zeroing the electronic balance while the beaker is on top, so that anything that's added, that means when we add the water, we would only be measuring the weight of water. There's no need to do any subtraction here. You no need to measure the mass of the empty beaker and then get it with the water and then subtract later. No need. You straight away zero it with the beaker on it, right? Okay, so basically this is our preparation. We already set to start the experiment. So what do you do to actually start the experiment? What are we going to do? What is the action that we do, that we perform to begin? We are going to immerse the object in the water, isn't it? That's the start step. That's it. So that's what we're going to do. When we start, okay, what we're going to do, immerse the slotted weight in water completely. Okay, fully immerse it. Must be completely submerged. Hold on. Okay, must be completely submerged. Okay, that's all. That's how you start the experiment. Now, once you've done that, then we have to start collecting data, isn't it? So what data do we collect from here? So remember, we are supposed to collect 3 pieces of data. 3. We need the weight in air, which we already did earlier. That is before starting the experiment. That's during the preparation phase itself. And then you need the weight in water, right? Okay, so we need to collect the weight in water. And you also need the weight of water displaced, weight of liquid displaced. Right. So we already collected weight in air. So there are two more things to collect. So that's what you have to write here, right? Now, after we've collected the data, that doesn't directly give us the MV and the RV. So MV and RV in this particular experiment has to be calculated, isn't it? We are calculating buoyant force using WA minus WD. And we are calculating the weight of liquid displaced by multiplying the mass with G. Both require calculations. So this is what you need to state at the observe and record part, whatever data we are collecting, data collection. Okay, so coming back here, observe and record. First, we say record the weight of the slotted weight in water. Okay, and then calculate the buoyant force. So now we have WA and WW. We can use FB equals WA minus WW. WA is here. That's why I say use the symbols. It will be helpful when you do your calculation and when you write down your formulas and all that. Okay, and then after that, calculate the weight of the displaced water. This needs to be calculated as well from the reading of the electronic balance. So again, don't assume that it is 10. If the question asks you to use 10, then use 10. But strictly in your paper 2 and paper 1, when nothing is mentioned, you should be using 9.81. Right? Multiply with 9.81. But if the question says use 10, then you use 10. Right? Okay, after that, we repeat. After that, we repeat. So this is only using 100 grams. So when you repeat, then you're going to change the slotted weight to increase the mass of the slotted weight. So how many do you need when you repeat? Generally, we have a total of 5 readings. Generally we have 5 altogether, 5 sets, 5 rounds of experiment. 5. Okay, so we started with 100, so you're going to repeat 4 more times. So the way that we write this is repeat steps, what to what depends on what you have. Okay, this depends on what you have. So repeat step 1 to 7. So it depends on how many steps you have. Follow your own steps. So repeat steps 1 to 7 using slotted weights of mass 200, 300, 400, 500, another 4, altogether 5. Okay. So this is your procedure. Done. So just use these 4 the framework. Use the 4 steps. Measure, prepare, start, observe, record, repeat, finish. You will cover everything. All right. Okay, let's go to tabulation of data. To tabulate the data from the experiment. Now, when you tabulate data, the most basic of tables will be first column MV, second column RV. This is the most basic of tables. However, every single data that we collected from the experiment must be tabulated. So sometimes you need to add anything that you recorded during the experiment must be in the table. It must be in the table. Okay, right. So again, think carefully. What is the manipulated variable? Oh, you don't have to think. You know the manipulated variable. You know the responding variable. Think about all the data that we collected. Try to do your own table first. Pause and do now. Okay. So if you've reached this point, I hope you've already tried your own table. But this is the header samples that are given in your textbook. Okay, let me point that out first. Okay. So here you can see what is the MV? MV is weight of water displaced, right? So MV is here. However, MV is not measured directly. It is calculated, right? So what I personally would include in the table would be the mass of the slotted weights first. In your textbook, it doesn't begin like that. But if I was doing the experiment, that is what I will add. I will add mass of slotted weight first, and then you do the weight. So how do you do the weight of the water displaced? Oh, sorry, this is the other way around. This is the other way around. Yeah. Weight of water displaced would be the mass of the slotted weight times 10. So this one, again, please be careful. If they say assume it's 10, you use 10. Otherwise, you use 9.81. Okay? All right. So this is the weight of water displaced. This is our MV. Now, RV is buoyant force. Okay? Once again, buoyant force is calculated. It is not measured directly. So we need two readings for that. Weight in air and weight in water. Then you do the subtraction. Everything that I've done in bracket here is the calculation, right? Because we don't have the actual data here. So this is the calculation. Okay? So this is calculation. So weight in water, weight in air, subtract. Subtract. You must always get a positive value. Okay? Now, few things to note here. In your header, you must have the unit in the header, right? It cannot be with the data, number one. Okay? If not, you will straight away lose 1 mark. Out of the 3 or 4 marks for the table, you will straight away lose 1 mark. Doesn't matter if your header is correct. Secondly, when we are using spring balance, notice what is the smallest reading on the scale. The smallest reading of the scale will be 0.1 Newton, isn't it? Okay, when you're using the instrument, always check the scale. The smallest reading is 0.1, which means all our readings must be to 1 decimal place. Must. Even though it may seem like it's like for example, 1 Newton, you can't just write 1. You can't just write 1. You won't get marks. You have to write 1.0. Follow the accuracy of the instrument that you are using. So follow the smallest reading on the scale. 0.1. So therefore 1 decimal place. 1.0, 2.0, like that. Okay. Now, this one, you please use the data that you get from the experiment. Yeah, don't just use this. Okay, I'm just assuming that it is 10. So I did, for example, the mass of the slotted base weight is 100 grams. So 0.1 kg times 10. That's how I got these values here. You don't use this. You use, because you will be actually weighing it. So you use your experimental data. All right, use your experimental data. You won't get exact numbers like this. Okay. Okay, so this is table, right? Okay, then we go to the graph. So draw the graph of buoyant force against weight of liquid displaced. So when you draw your graph, first when you plot your graph, you won't get a perfectly aligned set of points. Right? You won't get perfectly aligned set of points. Okay, so number one, you must label your axis properly. Y-axis and x-axis must be labeled properly. So I'm going to show you that here. Okay, so y-axis will be buoyant force. Okay, so we just put it there. And then x-axis will be weight of liquid displaced. Now, this is not complete. What is missing? I hope that you realized it right away. What is missing? Units. Units are missing. So weight of liquid displaced, put brackets, Newton. Buoyant force, bracket, Newton. Please make sure that you have this, right? Label the axis, put in the unit. Okay, now once you plot your points, right, you will not get perfectly aligned points. So you might get this, and then here, and then here, and then here, and then maybe the last one somewhere. Okay, maybe here. Okay, so now you need to draw line of best fit. Line of best fit, there must be two things. Join as many points as possible. Okay, join as many points as you can. So here I can only join a maximum of, according to my data, I can only join 2. Okay, so choose the 2 properly. So how do you choose which 2 to join? So okay, let me join it first, then I show you. Okay, so this is my sample answer. Okay, so once you have joined the 2 points, you must check and see all the points that are not joined. So for the points that are not joined, this is very close to the line. This is good. But you can see there's 2 at the bottom here that's very far away from the line. It's not balanced. It is not balanced. So the number of points that are left on the top and bottom, first of all, must be balanced. right? In this case, there are 3 points left. So either 2, 1 or 1, 2. It must be balanced. You can't balance it perfectly because it's an odd number. But yeah, you have to balance it. So, and another thing is the distance of the point to the line, the perpendicular distance must be as short as possible. So this is not a suitable best fit. This is not a good best fit. So I need to test again. So then I try, let me try joining maybe these two. Okay, so for example, if I join these two, now this is more balanced. This is more balanced. 1 on top, 2 at the bottom. Yes. The distance, the perpendicular distance to the line is roughly the same, top and bottom. They're all around the same. Yeah, this would be a better best fit. This is just a sample answer, right? Okay, so I hope you understand best fit. Now, the next question will definitely be 99.9%. Explain the relationship based on the graph. Now, this part is very important. This part is very important. From the graph, based on the graph. Don't base it on your theoretical knowledge. Do not base your answer on your theoretical knowledge. Base your answer on your graph. Okay. Now, we know it's directly proportional, theoretically. Okay. But according to the graph, is this directly proportional? You can try and extrapolate your line at the back. Is it passing through the origin? No, it's not. If it is not passing through the origin, then you cannot say that it is directly proportional. You can't. So if it is not passing through the origin, what relationship is this? We say that y increases linearly with x. Do you remember this format? This is your Form 4, Chapter 1. Right? Okay, so that's exactly what we're going to say here. So we are going to say that the buoyant force from the graph, based on our graph, buoyant force is not directly proportional. It is not directly proportional, but it increases linearly with weight of liquid displace. This is how you do it. Okay. If in your graph you really got a line that passes through the origin, no problem. You can say buoyant force is directly proportional. Not you can. You must say buoyant force is directly proportional to weight of liquid displace. Okay. Oh, one more thing, class. Just make sure that this is your RV. Yeah? RV should be on the y-axis, and MB should be on the x-axis. Okay, MB should be on the x-axis. Yeah. So this is how you do your graph. This is how you interpret. Now, this particular question, there is an interesting thing here. Calculate the gradient of the graph. So for this particular question, this is important because, right? Because from our understanding, buoyant force is equals to weight of liquid displace. Actually, this is the actual relationship. This is the actual relationship. It is equal. It is not just directly proportional. It is in fact equal. Right? So, what gradient do you think you should get? If we use linear law, this is your y, right? Right? This is your x, isn't it? So capital X. Your C is 0. Okay. So, what is M? M is 1. So, the gradient of the graph that you should get, you won't get exactly 1, but it should be close to 1. Okay. Should be about there. Theoretically, the value is 1. All right. Okay, guys. I hope this video has been helpful. I will be posting videos on physics and chemistry and biology as well. Please look out for that. Share it with all your friends. Okay, if you have any tips for the exam, also please share in the comment section. Let's help each other out. Let's everybody help each other do the best that we can. Okay, I wish you all the best. Those of you who want to continue your exam preparation in my classes, just go to mrrueltuition.com. You can join the exam drill classes. I'm also covering the last few topics in my Form 5 classes, so you can join whatever you want, whatever you need. Join whatever you need. All right. Okay, guys, all the best. I really hope that you get your dream grade, right? All the best.